Before we begin, let me just show you this on Firefox. Yeah, so I posted earlier today an updated version of the list of problems. I mean, I basically just added like one or two. So there's not much that I added. And then what I did add was a little bit of an answer key. So like the majority of them now have like next to each of them like at least the numerical answer for the problem in the case of um, uh, like of those problems that have a numerical answer. So yeah, so basically what I will do is that once we have a quiz, as I said, the quizzes will be based on the problems from this PDF. So after the quiz, I will give you like more like detailed solutions for the quiz problems. So you will get more like something more informative about the solutions. But I mean, for most of these problems, like the good thing about probability theory is like that, if you definitely don't have the right setup for the problem, like the numbers that you get will be completely different from the correct answer. So it's not like one of these things where like maybe you can be off by a little bit. Typically, it works or it doesn't work. So like it just by looking at the numerical answer, you have like a pretty good sense of whether you did it correctly. Um, what I was going to say is that let's see. So I did create. Someone reminded me earlier. I just created like a practice quiz. So this practice quiz is just for those who have never used Respondos before. So again, like the quizzes will be usually like during the last 30 minutes of class when we have a quiz. So the idea will be like, we have like a regular meeting for the first 90 minutes, and then I'll make the quiz available, and then you just take it. So you will leave the Zoom meeting and take it through Canvas. The thing is like for the quizzes, we will use responders. That's just because that's what we will use for the exams. So just for a way for you to practice using responders. So the idea will be when you take it with responders, like it kind of it locks down the browser and everything else. So you just have to have like your camera activated and other things. And yeah, once you're done taking the quiz, then you'll have a couple minutes to I'll give you like I'll usually give you like 15 minutes to upload the solutions to Canvas, if that sounds good. The quizzes will be like 2 or 3 questions every time, so like the upload shouldn't be take that much time. Is that making sense? Are there any questions about this? So based on like today, what we cover on today, I'll like after we're done with today's class, I'll send you like an announcement letting you know what the problems of the PDF will be on the quiz. Like since it's like the first week and everything, I won't ask you to think about too many problems, like maybe 3 or 4, and then usually I also like to put one problem that's one example that we did during class, so that you have like some sort of incentive to go over the examples from class as well. So, but yeah, I'll send you like the announcement about the quiz problems once we're done with today's material. So if there are no questions, let me go to the iPad. Yes, I will after class. I will send the announcement. Yes, I'll for the correct for the quiz on Friday. Yes. And I guess on Friday I would give you the information for the quiz on Monday. So usually like at least you have like 2 days. But again, at least for the Friday quiz, since you have less time, I suppose like, yeah, it would be a shorter list of problems. Like, since again, like this is the first week, will probably be like 3 or 4 to go over. But like kind of like 3 or 4 representative ones. So it won't be too bad. I mean, it will be kind of like more like as just getting acquainted with everything, but uh, I'll send it after we are done with today's class, just to make sure of what we covered. That making sense? By the way, oh, I forgot to say this. So I do think for this course, like, I don't know if whether everyone has available like a calculator or not. I do think it makes sense to have a calculator available during the quizzes. Just I will let you like enter the answer like without doing the multiplications or things like that, but it is useful just to get some intuition in these probability problems to actually enter the numbers to make sure that they make sense. So I do think it will, like, if you want to use a calculator during the quiz, that's totally fine. I mean, I won't write the quizzes in such a way that is required, but it's just useful to have one available. So unless I change my mind, let's just keep it at that for the quizzes, and then just do. So don't, like, just for something for you to think about. Because really, like, you don't get like a good sense of what's going on unless you actually put in do the actual multiplications and operations that are involved with these problems. So okay, let's begin. Like many of these probability problems, like as I said the first day of class, there are not that many formulas, and each formula is relatively simple. Like, what's kind of interesting in the probability problems is just to decide which formula to use to begin with, and just to have like 1 or 2 examples that kind of seem very convincing, and from there you kind of extract the formula that you care about. So let me I prefer to start with an example instead of like just giving you like a formula, like trying to come up to build up the formula, if that makes sense. So again, this is like these are fun problems to think of, especially at the beginning, which are like called combinatorial problems. So I don't like to like kind of just spoil the answer, if prefer to give you like a little bit of time to think about it. So let's start with an example. So let's say you want to build words in English. Okay, and so just to make it clear, what do I mean by 4-letter words? I mean, first, that they don't need to make sense. So for example, something like what would be like a 4-letter word? This will count for us as a word. I don't think above is an actual word, right? So I mean, in a sense, like, it makes sense. Not that I can recall. So like it does, like, it is not like a proper word in English, or it doesn't have like a definition, but it's still like a word in the sense like you're using the letters, from the alphabet, and it just has four letters, right? So something like this count. And what else? So we're not going to distinguish between lowercase and uppercase letters. So something like this counts as the same as the previous one. Okay, so is that making sense so far? So good, the setup. So how many symbols are there in the alphabet, or how many letters are there in the English alphabet?
$26.
Yeah, I think it's 26, correct. So we have like kind of 26 letters to play with, right? So we have 26 letters. Right? And we have kind of 4 boxes or 4 like entries that you can put these letters in, right? And notice that I'm allowing repetitions, right? Because even like words in English which do make sense can be, can have like repeated letters. So that's totally fine. So, I have 26 letters and I can place them in 4 spots, and I'm allowed to repeat one of the letters. So again, like the good thing about these probability problems is that many times you have like an intuition for what the answer should be. So anyone want to has, I guess, yeah, it's just 26 to the 4, right? 26, 26, 26, 26. Is that making sense with everyone? Everyone is convinced. It's kind of one of those things like you're either convinced or not, right? Like I mean, there are other ways to try to come up justify why they should be 26 to the 4, but maybe it's easier to make a. It's more convincing maybe if you make it with just 2 words first, right? If you make it with those just 2 words, then it should be 26 squared, and that is more easy to visualize because like you can do it kind of like a similar array from last time, in the sense that you could write like A, B, C, D, E, F, G, right? And then you start singing the alphabet. So you put it like this, and then you see like in the matrix or this Excel spreadsheet, you can just put A, comma A, and A, comma B, and so on. And you see like this would be the word A, B, the other would be BA, and so on. And that has 26 times 26, 26 times 26 entries. So what happens when it's happening with 26 to the 4 is that it's not like a square or not even a cube, but it's some sort of like hypercube, right? Where it's like, uh, vertical, like a vertical axis, horizontal axis, like, and then 2 more axes where you're like putting like everything like in a spreadsheet. Is that making sense? It's like a multi-dimensional spreadsheet. Is that right? Every letter has 26 possibilities. What I'm trying to emphasize here is like it is being multiplied. It's right. It's right. It's not 26. The important thing is kind of to realize here it has to be 26 plus 26. Sorry, it's 26 times 26 times 26 times 26. It's not plus, right? So, and that's kind of what makes probability interesting, because the options just multiply, right? They don't. Most of the formulas involve multiplication instead of addition. That's what I'm trying to say. Um, and this is what I'm saying also, where like it's kind writing 26 to the 4 is okay, but it's not. It doesn't give you like the full grasp of how many words we're talking about. So that's why I'm saying like it's fine to like use some calculators to have some actual intuition for what's going on. So if you like put on your calculator what 26 to the 4 is, that is this number. So it's almost 500,000 words, right? And that's a huge number of words, right? If you think about it. So that just shows you how quickly things can grow in these problems of, this is what is typically called like a combinatorial problem, because you're just combining things together, right? So here we're just combining letters among themselves 4 times. But this should just give you like an idea of like how big these numbers can end up becoming. So is that making sense?
Yeah, no problem.
And then just to give you a sense of how much it is, like, so I Googled this to make sure. The Milky Way has an estimated, like, right, so the Milky Way is like the galaxy we live in, just in case. So the Milky Way has like an estimated number of like, well, let's put it like 10 to the 67. It's a little bit more than that, but like 10 to the 67 atoms. Okay. So that means that if you did use word to write words, I mean, you can think that you are introducing a symbol for the words, which is like a space. So think of adding like a symbol of a space for like to separate words so that you can talk about sentences. So if you thought about like sentences with 67 words, with 67 characters or symbols, already sentences with 67 symbols, which is not that much, right? Like a sentence of 67 symbols or letters is not such a big sentence, right? That already has more, like, that number is already bigger than the number of atoms in the entire Milky Way galaxy. So if you, and you must imagine like that a letter, a single letter, to print a single letter or to type a single letter on a computer, that requires millions of atoms for it to be actually written out. So it's basically impossible to print a list of all these words, like realistically speaking. And we're just talking about very small, we started with very few symbols and very few, the length of the words are it's not that big. So this just gives you like it's just kind of like unless you put it in those terms, you cannot really like appreciate how big these things grow. Is that making sense? So it is like, we're talking about humongous numbers. So and just to give you another warm up, we're starting just with warm up examples before I give you like a formula. Okay, so how many 4-letter words could you write? So here's the example or a modification of this problem. So part 2 of this problem. How many 4-letter words are there? If what? If you want, say, if you want the first and third letter to be about a vowel. So a vowel, what? They are A, E, I, O, U, right? So, and everything else is the same. I'm allowed to repeat letters, no difference between lowercase, uppercase. So still we're working with 26 symbols, but I just want on the first and third slots that on those 2 slots, whatever I put is a vowel. So here there must be a vowel. Yeah, good. Perfect. So again, it's kind of like a bag. You kind of like you have all these letters from the alphabet. You grab like a letter and you have to drop it on the spot. So here you can drop 5 different things. Here you could drop 5 different things, right? I'm not giving you any restrictions on the second and fourth spot, so you can still drop any among the 26 possibilities, right? Is that making sense? So I'm claiming that the number of options available is like 5 squared times 26 squared. Is that making sense? And again, if you give me this number, it doesn't make a lot of like intuitive sense to me what this number is. Like you actually have to enter it, like do like try to do some sort of multiplication, like to see what this looks like. That's kind of what's interesting. So if you, I like to use Wolfram Alpha just in case. So if you go to Wolfram Alpha, that gives you 16,900. So it's almost 17,000, right? But that's way less than almost the 500,000 options that we had before. So again, this is just trying to get you like to get used to like how much like the differences can be once you start imposing some conditions on how you want to build things, right? So like you drop from 500,000 almost to 17,000 in the number of options. Is that making sense? So like you can think of what I was trying to say last time is that in the classical notion of probability, the one that was developed earlier by in the Renaissance and scientific revolution, industrial age, kind of if what they would have said is like if you want to find out the probability, then that among all these words that we had found computed before, you would choose like you would grab, imagine that you put all these almost 500,000 words in a bag, like or an urn. That's kind of like a lottery game, right? Like you have like a ball representing each word, so you put them all like in an urn, and then you would ask, well, what's the probability that you would like grab at random like one of these words that has this condition of first and third letter to be vowels. So the probability in the classical definition would just be the ratio between the number of favorable outcomes versus the total number of outcomes. So let me just write that down. So the probability. So in the classical definition of probability, the probability of getting a word with a vowel in the first and third spots among all the 4-letter words would be, again, you consider the number of positive outcomes. So the number of positive outcomes was 5 squared to 26 squared, and you divide by the number of total outcomes possible. The total number of outcomes possible was 26 to the 4. And I'm writing it this way just to show you that there's simplification. If you write it like after doing the multiplication, it's less clear what you can cancel or how can you simplify these expressions. But if you write them in power notation, it is easier to know how to simplify, right? Because this is just like 5 divided by 26 squared, right? And then that something you can put, like, again, if you want, it's better to have like actual numbers for everything. So if you do the calculation, that gives you 0.036 approximately. So usually when I write these symbols, which it looks like the equality symbol, but it's not quite that. It's kind of like a weakly equality symbol that just means approximately equal to. Okay, so that means that there's almost like almost like if you want to round up, it's like 3.5% or 4% chance of like getting one of these special words out of that all the 4-letter words. Is that making sense? Any questions up to this point? So, I mean, this is sometimes called the basic accounting principle that, let me write it down. You can phrase it in terms of experiments or like results. The book, if you're following the book, they talk about experiments. So I'm just going to use the words experiments. Possible outcomes. Then in total, there are like, if you want to know what are all the possibilities, if you kept track of all the experiments at once, you just multiply the different options to get the total number of possibilities. Okay, so I mean, it's kind of just saying what, like the example that we were doing before. I don't necessarily, sometimes I don't think like these formulas are too illuminating unless you have like an example next to you that clarifies things. So this is just saying it's like something can happen in n1 ways, another thing can happen in n2 ways, a third thing can happen in n3 ways, then all of these together can happen in n1 times n2 times n3 ways, which is kind of what you were seeing here, where our ways were like how many letters we could put on each, and how many letters, distinct letters we could put on each entry of the word. So it was 26 words times 26 times 26 times 26, for example. But in practice, you know, you kind of recognize it, and then you just use it. You don't have to think too much about this. Is that making sense? Any questions about this? I mean, again, this is kind of, I think it is fun, especially when you compare, we'll do something like less intuitive things by the end of today. So you'll see these can be quite powerful. But let me do another example because this is a slight modification of the previous one. So let's do example 3. Did I indicate that today's lecture 2, by the way? Yeah. Here's example 3. I have 5 books that you see here, and imagine I have like a bookshelf and I just want to organize the books, but I'm going just to put 3 on the bookshelf, right? So let's say I have 5 books, they're all distinct. So I have these 5 distinct books. So you can think of it as a ranking. I'm just going to decide what's the first book, the second book, and the third book in the shelf. So I'm going to put like a book 1, book 2, book 3 on the shelf. So in how many ways can you organize 3 of them? So I'm just going to keep I'm just going to use 3 books, but I can I have all of the 5 can be graphed, right? So just yeah. I was correct. It is for the first slot you have 5 options, right? For the second slot you have 4 options, and for the third slot you have 3 options because I'm not allowed to, once I decide to put one in a spot, like that book is going there. So I'm not allowed to kind of reuse it. And that's like the slight modification compared to the previous example. Is that making sense? Is that okay with everyone? So that's 120 ways, right? Uh, oh, 60 ways. Thank you. Embarrassing arithmetic mistake. Yes, it's 60. What was I thinking? I was thinking with the case of 4 books, but yeah, it is 60. I agree. Good, thanks. Yeah, no, we're headed towards that interpretation actually. So okay, so right, let's see. But in this case, it's still, I mean, rewrite it in terms of factorial is kind of an overkill for this example. But yeah, like the next few examples will be in terms of like the factorial stuff. In fact, like okay, I can move to that modification of this problem. If everyone is so far so good with this example, right? So I'm just saying, like, it's, again, this kind of things make a lot of sense. but so there's not too much to discuss, but you'll see like this can become quite complicated once you start modifying the conditions a little bit. So you always have to just be sure of organizing things in the right way, so that it's kind of plausible. Okay, so here's like a modification of this example. So let's call it example 3.2 because I'm just going to tweak a little bit this example. So, and for this one, I'll give you like 3 or 4 minutes to think about it. So don't enter it on the chat until we rediscuss it, because like to give everyone like a chance to think about this one. So now I have 5 books. So I still have my 5 books from before, right? But now I'm just going to select 3 of them. Okay, so I'm just going to grab 3 on my hand, and I don't care how I grab them. So I'm allowed to like if I reorder them, I don't care because I'm just carrying them with me, moving them towards the shelf. So I'm still in the process where I'm carrying them to the shelf. So I don't care in which order they were, because then I would just rearrange them however I want it. So I have 5 books, but I just want to take 3 of them. To take 3 of them, but now I don't care about the order. So the question, and again, I'll give you like everyone like 2 or 3 minutes to think about it. So don't answer it even if you know. So it's how many ways can you do this in? Okay, so think about that. Let me just grab some more water and let's talk about it like in 2 or 3 minutes. Again, if you know the answer, just wait a little bit. Do not spoil it. So let's just discuss it like in 3 minutes. If you want to go quickly to the bathroom or just grab something to drink, feel free to do so. Okay, so anyone wants to give it a thought? What's the number in this case? Anyone kind of was able to figure it out? Let's see. So you're not sure. So you're saying 3 times 1 times. So let's see. Well, you're saying 10. Yeah, I'm not sure like if I understood the first one in the sense if you were multiplying them or so you're saying 10. I mean, it definitely cannot be more than 60, right? Because well, that's actually maybe how I should start explaining the solution. Like the difference between this example and the older example was that before I did care about the order, right? I cared about on the shelf. I do care about which one goes first, second, and third. Here, I don't care because it's like at the stage where I'm just grabbing them with my hand. So here's one way to think about this example in terms of letters. Like it's actually easier to think about it maybe in terms of letters. So it's kind of like if I had said like you have 5 distinct letters, right? Representing each book. So you could just be lucky that the first like it could be arranged by author, and so maybe you have 5 books where each author has like a different last name that starts with a different letter. So each of these letters is keeping track of each book. Okay, so in the past, right, in example 1.1, right, sorry, example 3.2 and 3.1. Oh my God. In example 3.1, like this would have been a selection of books, but this would have been a different selection of books, right? Because like here we do care about how they're being ordered, right? And this one would have been, I should probably do it in a slightly more organized way.
Is that making sense? So in the past, in the previous example, any of these would have been considered different, right? Because I did caring how I was placing them on the bookshelf. But now when I'm just moving them around, all of these are exactly the same 3 books. So they kind of all collapse into a single representation, into a, like, which you can just write ABC if you care. They all kind of become the same one in this interpretation. Is that making sense? Are there any questions about this? So what I'm trying to say is that in this example, like kind of for each of these 3 books, like they kind of were like 6 times more in the before. Why is it only 6 times? Because you had 3 letters or 3 books, right? And how can you rearrange them is like among themselves? How can you rearrange 3 books? Is 3 times 2 times 1, right? So this is which now become the same. Is that making sense? Are there any questions about this? So what I'm trying to say is that the number, the solution, the number of groups of size 3, that's actually how it's referred to. So the number of groups of with 3 books, the possibilities. Oh no, so good. No, yeah. So I meant the okay, I get you now. So yeah, I meant the more like just how many of the 5 books, if you grab 3 at a time, in how many ways can you do that? Yes. So if you it would be the previous example, sorry, the previous answer, 5 times 4 times 3 divided by 6. So that gives you 60 divided by 6, which is 10. Is that making sense? So are there any questions about this?
I'm not sure if this is right, but is this equivalent to saying like 5 choose 3?
That's what in a second, right? Like we're getting to a way to reinterpret this, but that's exactly the same way as saying 5 choose 3. That's what it will mean. Correct. Good question.
Awesome, thank you.
Here's another way. Okay, is everyone agreeing with this? Are we okay with this? Here's another interpretation, which is kind of, again, it's just kind of exploring all the different ways to think about it. So choosing which 3 books you want to grab, right, is equivalent to choosing the 2 books that are staying on the table, right? Like, let's say I have my books on the table, I'm moving them to the shelf. So choosing the 3 books that you want to grab or you want to carry is the same as deciding which 2 books are staying on the table or you're not carrying, right? Is that making sense? So then you can ask, well, in how many ways can I choose like the ones who remain here, right? So you had five books to begin with, right? So now you have only two, you have to select two. Those are the losers, right? Like the ones that you didn't want to take to the shelf, assuming that taking them to the shelf is a reward. So who is not getting rewarded? Well, you have 5 options, and then you would have 4 options, right? But then because we don't care which one, which one goes first in how I select them, you're kind of counting you're counting this number by 2, right? Like you're over counting by a factor of 2, because again, it's kind of like the same. AB and BA would refer to the same collection of 2 books you're not taking with you. So the number would be 5 times 2 divided by 2, which is 20 divided by 2, which is 10. Is that making sense? So that's another way to think about what about this problem. Is that okay with everyone? And then yeah, now just to introduce some more notation, let's just play with the original formula. So if you have the original formula was 5 times 2 times 3 divided by 6, right? So now I'm just going to rewrite it in a way that is actually more convenient. So I'm going to rewrite it as 5 times 4 times 3, okay, times 2 times 1. Let me just put in the different color, the new stuff. 2 times 1. Six is 3 times 1. Sorry, 6 is 3 times 2 times 1. And I mean, you're not allowed to, just multiply, add new things. So if you add 2 and 1 in the numerator, you should also put it in the denominator so that, it kind of ends up being the same expression, right? So here you're not doing anything. I'm just like re-expressing 6 as 3 times 2 times 1. It's a useful way to re-express it, because actually that's how we notice how many possibilities we had before. So this makes sense. Oops. And 5 times 4 times 3 times 2 times 1 could be something most of you recognize, because that's just what you call 5 factorial, right? Is that making sense? And this, it looks more close to the formula of like this 5 chooses 3. So let me just give you like a notation. So there's this notation called NR. This is like one of the most important, like this notation will appear all over the place in probability theory. So let me just like, it's like really important. So yeah, it's called like N chooses R even means N chooses R, or okay, so this reads N chooses R. And this is just n factorial divided by r factorial divided by n minus r factorial. And this is just, it is basically what we just computed. It's a number of the number of groups of R objects formed out of a total of n objects. So in this example, what we were computing is what you would call 5 chooses 3. So this means how many groups, if you have 5 objects to begin with, how many groups of 3 can you make? Is that making sense? This is like literally one of the most important formulas in all of like the probability course. So
Out of my own curiosity, does this relate at all to like binomial theorem? Any of that stuff?
oh yeah, actually yes, because it does appear in the binomial theorem. Yes, like maybe I should discuss that. Well, like it is like it is the coefficients that appear in the binomial theorem. If you what's like the formula is in the book, I actually think. Wait, let me just copy it for you. And not probably not that I was planning so this is the binomial theorem. Yeah, there's like if you maybe I don't want to get down the rabbit hole, but right now, but there is like there's like a proof of the binomial theorem that is kind of like an interpretation, a combinatorial interpretation, and so that's why you see the coefficients in front of x to the k and y to the n minus k equal this thing. I mean, basically what happens, like if you thought about it, I mean, it's kind of like dimensional analysis. Like if you thought that x and y have like units of length, right? Then this would have units of length to the n, right? Length to the n. So whatever you put here should have been like, should add up to n in the powers because they should have the same units. And then you just have to be like, well, how many ways can you, take it's kind of like depending on how you think about it, it's kind of obvious because now you have like you have like to get to n by choosing like x a number of times and y a number of times. So right, so it's kind of like choosing x you could interpret as a success, and choosing y could be interpreted as a failure. But it's kind of like, yeah, it's kind of like you're just grouping together the x's and the y's. So it is like, yeah, there's like this binomial theorem, you can think about it in terms of like a combinatorics problem, and that's why it appears very naturally there. Yeah, I don't know if I answered your question, but it is related to that. Yes, for 100%.
That answered the question very well. Thank you.
Okay, good. Yeah, no, it's like full disclosure, like these combinatorial problems are actually like, it's kind of like these things where whenever I think about them, I have to be super careful in what I say because it's not where like I have like the strongest intuition. So like all these combinatorial problems, I always have to be like super sure of what I'm saying because it's not as natural. There are other parts of probability that are more natural to me, like the ones that involve more of the calculus stuff, which we'll do later, like the continuous probability. But for these like combinatorial identities, I always feel like I could be tricked into believing anything, even though I'm not too careful. So that's why I always I'm like, well, let's just check first with a small example where like you're absolutely convinced that the answer is correct because you could make the count on your own. And once you do that, then you can extrapolate to the general case. But it like, this combinatorial stuff can be very tricky. So yeah, that's why I always want to be like extra cautious with this. But now we have enough tools to to say something, so to do something really cool, which is very non-intuitive, which is called the birthday paradox. So I can tell you about it. We can proceed to that unless there are any questions. And again, like this sorts of problems will be the bread and butter of the course. So we'll continue making tons, do a lot of examples involving this and choose a scale symbol and all this stuff. But so we're still like, you'll see like this will be kind of reused over and over. So yeah, if there are no more questions, I can tell you about we can discuss the birthday paradox. So are we good? Okay, so first, okay, or maybe just let's just start with it, and then I'll be giving you hints as we go along, because again, like kind of like the fun thing about these problems is just come up as much as possible with your own solution, because it's all otherwise it's kind of a bit spoiled. So imagine that you are in a planet where a year, instead of being 365 days roughly, is like just 7 days. So it's kind of like a year is a week, basically. So you have this planet where a year is just 7 days, planet X. So it's just like Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, okay? And here's the birthday question. So everyone is basically, everyone's birthdays will only land in one of 7 days, right? Because the year is just a week long. So the birthday question is, how big should a group of people be, right? So that there is at least a 50% chance, and here I'm going to emphasize at least, where 2 or more of these people will be born on the same day. So first, like, I don't know if like the question even makes sense, right? So everyone can be born only in one of 7 days, like on a week, basically. And am I asking how big should your group of friends be, so that at least there's like at least a 50% chance that 2 or more of of this group of friends will, 2 or more people in this group of friends will share a birthday. Okay. So just to give an example, what would be a very silly way to guarantee how big, what's the minimum size of the group of people that you need to guarantee with 100% chance, like with certainty. 100% means certainty, right? So how could you guarantee with certainty that at least 2 people in this group would share a birthday? How many would this group need to be? Yeah, it would just be 8, right? Because if the year is only 7 days long, I mean, the moment you have 8, like once you have 7, like you could have like this unlikely chance where everyone was born on a different day. But once you add 8, right? You're done. Like, the 8th person their birthday must go somewhere, right? That's a pigeonhole principle for those of you who know that name. But right, so I'm just saying, with certainty, like with 8 people, you would know that everyone like shares a birth. At least 2 people share a birthday, right? And here we're not asking for certainty. We just want like. So we're just asking, well, I just want like at least a 50% chance that 2 will have that birthday, the same birthday, 2 or more. So if there's 3, perfect, but at least I just want 2 to have the same birthday with a 50% chance or more. Well, it depends on well, if you say 11, then 100, that's true, but just because already 8 would make it work, right? So already with 8 people, at least 2 will share a birthday, and that's with certainty, right? So we definitely do want a number that's smaller than 8. Is that making sense? Well, okay, so you're saying that so okay, this is a good question. So let's start. Oh, right, no, yeah. Let's see. So let's ask it there, like that way. So if you have a group of people, if you have like a pair of friends, right? Maybe let's. So this is like a fun problem precisely because of this. So if you have just 2 friends, let's say your group is just 2 friends. So let me modify the problem a little bit. What are the chances that they will share a birthday? Again, a birthday can only happen. Well, okay, you're saying 4. This is like a number that seems a better one. Now, do you have like a argument for why it should be 4? But in any case, yeah, please talk.
It's just applying like the formula. I mean, like, so the formula is like what? 7 times 6. Because okay, so that's like 7 days, and each person can like have birthday in like any of the 7 days. So we have like the possible outcomes, like the sample space is just 7 to the power of n.
Right.
And then everyone can have a birthday in 1 day.
Right.
So it's just so we put like 7 people in those days. So it's like 7. And then the next day we'll have 6 people. So 6 times 5. So we just do 7, 6, 5 until 7 minus n plus 1 divided by 7 to the power of n. And then you just have to find an n where it's greater than 1 over 2.
Yes. Okay, perfect. You are basically giving the right answer, but let's just start with in case everyone, because like that explanation can be confusing, like if you see like without any context. So let's start with actually like just the case of 2 friends, and then we'll explain why 4 works, as you're saying. So if you just have 2 friends, the better question would have been, what are the chances that they share a birthday? That's a lot more like a lot easier to understand, right? So well, if you have only 2 people, right? you could make a table if you want, like, you know, there are only 7 days. So the grid has like the grid has 49 options, right? 7 times 7 is 49, right? So the total number of options. So the total number of options are 7 times 7. So this is 49 options, right? Possibilities. And then sharing a birthday, what would it mean? It would just mean like having your birthday coincide along the diagonal, right? Is that making sense? So sharing a birthday has to involve the diagonal. So that would be 7 outcomes which are favorable, right? So the probability, again, remember, like the probability is the total number of favorable outcomes divided by the total number of possible outcomes. So the probability of 2 friends to share for sharing a birthday is just 7 over 49. So it's 1/7, right? Which is that, again, if you no, saying 1/7 is okay, but it's not that useful. So let me put it like here. So that is about 15% chance. Or 14% chance. Is that making sense? But okay, so that, for example, that tells you that having 2 people would not have been good enough, right? But there's a more useful way to think about it for like the generalization when we have a group of more people. So an alternative way to think about this, right? And it's a better way to, an easier way to ask it, you'll see for the generalization. Is let's find first the chances that your 2 friends, these 2 people, have different birthdays, right? What are the chances of them having different birthdays? So having different birthdays is the opposite condition of having the same birthday, right? So this is better, this is nicer, it's easier, it doesn't even require a visualization because the first friend would have 7 options, right? And the second friend would have 6 options, right? Because now we cannot repeat the birthday. So that just gives you 42 options, right? So the chances are the probability would of having different birthdays. Oops, the kitty is like playing with the plants. Probably should keep her away from them. So the probability of having different birthdays. Oh, and now she wants to type on the keyboard. So probably I'll move her downstairs. So is 42 over 49, which is 6 over 7. Well, and that's what, I mean, that's what's going to be 6 over 7. That's, I mean, it's the complement, right? If you think about it. So 0.86 approximately. So once you find is that making sense? So instead of finding once you know that the probability of having two friends having different birthdays is like 0.86, the probability of having the same birthday is 1 minus that. So let me write it here. Probability is 1 minus probability of different birthdays. Is that making sense? So that's why you end up with the same number, which would be roughly 1 minus 0.86, which is 0.14. Is this plausible? Like this, if you're, this is what I'm saying. If you're convinced of the answer in this with these small numbers, you will know how to generalize this. So it's always important to understand this first with small numbers before doing like the actual game with real numbers. So let's just again, let's just take it a step at a time. So what would happen with three friends? It's kind of fun. If you had like now with three friends, a group of three friends. There are a total of 7 times 7 times 7 outcomes. Right? Because so that's the total possibility, that's the total birthdays where we're dealing with 343 outcomes, different arrangements for the birthdays of each person. And what's the probability that all of them have different birthdays? So let's try to, when do all of them have different birthdays? Well, it would be 7 times 6 times 5. Is that making sense? Okay, and that gives you 7 times 6 times 5. And that's 210. So there are 210 cases where they all have different birthdays. None of them has, they all, like one is Monday, the other Tuesday, the other Wednesday, or one is Monday, the other Thursday, the other Friday, you know, all of them landed on different birthdays. So the probability of different birthdays for three friends to have different birthdays is 210 over 343. Okay. Which again, I don't, if you give me the number, I don't know what that means. Like I put it on the calculator, that's about 61%. So that's the probability of different birthdays. Oh, no, she's like in the chair. And then trying to destroy plants. So and so the probability of having the same birthday is what? 1 minus 0.61. Well, I don't know to what extent they're helping you type them, because I'm sure like they just randomly will enter the keyboard. So probably yes, there's some they like to destroy things, especially when they're a young age. That's the fun part. Okay, so already once you have three friends, a group of three friends, there's a 39%, roughly a 39% chance that at least of them having the same birthday for at least 2 of them. Is that making sense? And now we finally get to this magical number of 4. So for 4 people, we have 7 to the 4 possibilities, right? We have 7 to the 4 options, right? That's a total, like the way you could like give like a different birthday, like, you know, you could, like, you have 4 people, like each has to be born somewhere someday. So like that, this is like all the possible combinations of that. Okay. So that's almost 2,400 options, basically. And when are the 4 people going to be born on different days? It would be 7 times 6 times 4 times 5 times 4. Okay. And that's 840. So the probability of being born on different days is 840 over 24/1, and that gives you about 35% chance. And so what does that mean? That means that there's already a 65% chance that with 4 people to have the same birthday. So if everyone were born on a week, once you have a group of 4 people, it is more likely than not that 2 will share the birthday. Is that making sense so far, so good? Oh, like you mean directly? Like instead of like, oh, actually it's a lot more complicated, which is why I'm going this way. Like, and I would need to think about it because remember the condition is that at least 2 would have it. So you have to kind of compute the probability that exactly 2 people have it, the probability that exactly 3 people have it, the probability that exactly 4 people have it, and so on. So it is more, I mean, we should get back to this, but probably when we have more tools. But it is a lot harder. Like, yes, it is it's a brain fog. It is like, yeah. Because it's saying at least, so you have to, I promise you don't want to do that. So this is, but it's so much easier when you think about it. No, let's just ask first in how many ways everyone is born on a different day, and then you just subtract 1. But I'm like, and this is actually like a very useful trick, but it's kind of surprising that it can be so powerful. And it will become more clear once I give you some of the rules for computing probabilities. But it's kind of like one of these things that happens, like where like if you just phrase a problem in a different perspective, which is exactly the same problem, it just becomes like infinitely easier. Like it's kind of a weird thing that maybe you really haven't experienced before in mathematics or in many classes, but here it just becomes very common. Like, and here's like that cool thing. So, well, the easiest way to find this, the easiest way to do the probability of the same birthday is this way, because just because if you want to do like a direct approach, it's what I was saying. computing the probability of having two with at least the same birthday means the probability of having two with the same birthday, or the probability of having three with the same birthday, or the probability of having four with the same birthday, and so on. So it's like a sum of probabilities. Well, it's just well, it depends on what you mean. 7 plus 4. I'm just saying that if everyone were born, if you could only be born on 7 different days, once you have 4 people, then at least 2 will have the same birthday with at least a 50% chance. But what I'm saying is that it's just easier to attack that problem to ask in how many ways everyone could be born on a different day. Yes. Now, here's okay. Well, let me check first if there are more questions about this before telling you what is really cool. So is this more or less clear? Like so far so good? So what's really cool is that if you add, now you can ask the same for an actual year, right? I started with the example of the week because everything is just numbers we can work with more easily. But now let's say that a year is an actual year. Now a year is actually 365 days. So we come back to Earth. Now, what's the number of people you need so that at least 2 of them have the same birthday? With a 50% chance or more. So what do you, okay, and this is kind of like an opportunity to just give like whatever your gut feeling says. So how large do you think this group of people should be? Like just going by basic intuition.
I had a feeling it would be like 183.
Right, you're
Because-
just going by half, right? You're just dividing by
Yeah.
half, which is, of course, what everyone should answer, like as a gut feeling, right? Like that kind of seems the most reasonable option, but anyone has like another, and like it kind of seems reasonable in the week case, right? Because if you divide 7 by 2, that gives you 3.5. You cannot have 3.5 people, so you round it up, so you get 4, right? So at least in the case of a week, that seems like a good like guess, right? So does everyone think that that should be the anyone wants to? Right, this is exactly kind of like it gives it away with the name paradox in front of it. So the paradoxical fact is that maybe you can actually make a guess that is a lot smaller. So it is, you don't need actually 185. So what would be a smaller number that you think could be? I mean, that's what makes it well, right. Unless you Google it, right? That's like the perfect guess. So it is 23 people. You only need 23 people. So if you have a group of, if you have 23 friends on in your group of friends, there's at least a 50% chance. Yeah, no, because it's so weird, you know. There's at least a 50% chance that 2 or more will share a birthday. But you should just think about how much smaller that number is than what you would have expected, right? Like in the case of the week, like kind of the answer is very intuitive, you know, it matches our intuitions, but already for a year, we're completely off from what you would have naturally expected, right? So the paradox is just to, you know, realize how much the actual answer can be from what we expect. So before like actually trying to explain why it has to be 23, let me just show you, because there's a really cool website. I'll post the link on the Canva site if you want to play with it, because it's fun. It's fun to, you know, try some numbers. So do I have it here? Is this a one that I'm sharing? Which no, I'm sharing. Oh yeah. So there's a really cool link to this one called Understanding the Birthday Paradox, where you can play with some experiments. So for example, like what we started with was with 7 days, right? Like the year was a week. And if you have 4 people, you had at least, you know, there was a high enough chance of more than a 50% chance of like getting the correct answer. So if you put 365 days, it is, yeah, it is more or less, it is related to that, but we have to go into the details to see what's really happening. But it, but yeah, it's close to that. It's more related to the fact that we're everything in probability kind of involves multiplication, and multiplication just grows things like we typically say exponentially, but it just has, you know, grows things very, very large. In this case, it's not exponential growth, but it is very, very large. And here, if you had like 365 days with 23 people, like the probability is just a tiny bit amount of over 50. But then you do something crazy and you're like, well, let's say that a year had like 10,000 days, right? That's the fun thing. You say a year has 10,000 days. And if you try like, what does it seem to be here? Oop. Okay. It looks like if you try 119 people in that group, it seems to be more than enough to have at least a 50% chance. So like this is even more surprising, you know, because now you have 10,000 days and it's just like, you know, 5 times, roughly 5 times more than what you would have needed for like ordinary year. So it, you know, it's kind of like the fun thing here is kind of to understand what's happening. So are you ready to see why this works the way it's supposed to work? So let's try to see it. But it's kind of fun. I mean, I think this gives like a really good flavor of what makes probability like a non-intuitive thing, you know, many times. And just like explains why people are not used to large numbers. Like what's happening here is like multiplication can turn something like, you know, can grow things very quickly, and we don't have really good intuitions like our brains for what those numbers really mean. Why is this true? Okay, let me try to say, there are different ways to explain it. Hopefully this will make sense. So let's say that n is a group, the number of people in your group, right? So how many total options do we have here? Like we have done this many times, so hopefully, what should be the total number of options here? All the possibilities that you could make with n people for all the possible birthdays that they could get. Perfect, 365 to the n. Is that making sense with everyone so far? So good. And now, just as before, let's count the options where everyone has a different birthday, right? So let's count the options, number of options where everyone has a different birthday. So what should I put here? I should put like 365 times 364 times 363 times. What should be the last number I put here? What should be the last entry? Well, you'll see it's not graphing n factorial versus n, but right, of course, like it's less than that. Like that would grow super faster than the actual growth that you're about to see. But so what should be the last? What would someone put here? Oh yeah. Oh, n to the n. Yeah. Right, but it's more or less like that. It's slightly modified, but yeah. So for example, yeah, perfect. Let's just check that this makes sense, because you know, if your group had like 3 people, right? Oops. If the group has 3 people, then the last number should be 363 in this product. So you put n equals 3 here, you get 362, and then to get the correct number, you have to add 1. So yeah, you're multiplying from 365 to 365 minus n plus 1. Is that making sense? That's why I wanted to start first with very small numbers so that everyone could develop an intuition. But then the fun part is always to do the general case, which is kind of what we're doing right now. So with a probability, right? Like the probability in this case of everyone getting a different birthday is that number divided by 365 to the n. Is 365 times 364 times 363 dot 365 minus n plus 1 divided by 365 to the n. Is that making sense? Questions up to this point? And we want this to be less than 0.5, because if this is less than 0.5, that one minus the other probability will be more than 0.5, and that will be the, where they at least to share a different birthday. So it's just easier to ask for this to be less than 0.5. Is that making sense? Want this less than 0.5. So that the other one, the complement, is more than 0.5. Is that okay with everyone? So one, like the brute force method would be to take 365 times 364 times 363, and notice that when you put n equals 23, when you do all this huge product divided by all these 365 to the 23, you end up getting a number that's less than 0.5. But that's not like, that's okay, and that works, but it's not the one that's like most illuminating, because you're like, okay, how in practice are you even going to compute that? Even like for a computer, like I guess these numbers can get quite large. So it's not something that you would like to try on a computer like directly necessarily. Like it can really run off, you know, like the exponents like grow so quickly, as was mentioned on the chat. 365 to the n grows so quickly that it's not so I don't recommend like just doing the entire product, if that makes sense. So there's like a way to think better of this formula, and that's kind of going to be the key for everything. Oops. So here is like a more smart, more intelligent way to think of the same formula. So this formula, right? First, like let's just put the numerator in a way that has kind of have this format. So in this format, you always have the number 365, and you just put something that you're subtracting. So let me just rewrite this as 365. What is 364? That's 365 minus 1, right? What is 363? That's 365 minus 2, right? And then the other one is 365 minus n plus 1, right? So now this has the advantage that every factor looks like more similar, because it's kind of 365 minus an integer you're subtracting, and what you're subtracting is increasing. Is that making sense? So the first thing that I'm doing is kind of, you know, harmless, but it's actually very useful. So I'm just like rewriting each factor that appears in the product as 365 minus something. And then how many factors are there here? There are actually n factors, right? Because there's a group of n people, right? So there are n factors here. And then there's this 365 to the n, which we kind of like all assemble it together, but there are n factors of 365 downstairs, right? So now the next step is kind of to, you know, spread it out. So let me see if this makes sense. So I'm going to write it as a bunch of mini multiplications. Is that making sense? So I just broke the huge products into mini products. Is that okay? So the denominator is still 365 to the n, and the numerator is still this stuff. It's just I'm breaking it into mini pieces. Okay? So far, so good. Well, at least we do know what's the first fraction. What's the first fraction, right? Just one, right? And then what's the second fraction? Well, the second fraction is, I'm going to write it in a way that looks a little bit complicated, but it's actually useful. It's 1 minus 1 over 365. And then this is 1 minus 2 over 365. And then 1 minus n plus 1 over 365. Oh, let me write it. Well, yeah. this minus is only affecting the n, so the 1 is outside the 365 here. Or okay, if you want so that it looks the same, I'll put like the minus in front of everything. So this would be n minus 1. Yeah, it looks better that way. So I'm factorizing a minus 1 there. Is that making sense? So far, so good. I don't know how many I have lost by now. Is everyone agrees? I mean, I'm just rewriting things in a very, it's not so clear why I'm doing this, right? Of course, I'm doing it for some reason, but like maybe at this point you're like, okay, yeah, how could I have ever thought about this, right? So I'm not saying that you would have needed to think about it. I'm just saying like, I'm just trying to give you like a way to observe why instead of doing like the brute force approach where you just compute everything, like this will be more interesting. Okay.
Is this sort of similar to like when you can rewrite like x to the n minus 1 as x minus 1 times x to the n minus 1 plus all those other things? Something like that?
Yeah, it's kind of like that, right? Yes, it's more or less like that. But now what I'm going to do is something that again is kind of like, why would you ever think about this? But yeah, at this point it's kind of like a rewriting. It's kind of playing with algebraic identities. Like that's one way to think about it. Now here's like the cool thing. Like I mean, like how could you ever think about this, right? But who remembers the Taylor expansion for e to the x?
It's like 1 plus x squared over 2 factorial plus I think x cubed over 3 factorial, so on.
Perfect, yes. Okay. So what is e to the minus x? E to the minus x plus, sorry. Plus. So e to the minus x is just replacing what you get. Is the same Taylor expansion, but you replace x with minus x, if you remember how you did that. So it becomes 1 minus x. Well, minus x squared is still x squared over 2 factorial. Then the other one is minus, now it becomes minus x cubed over 3 factorial plus. Is that making sense? So what does that mean? If x is really small, if x is small, that means I will do something completely like crazy and I'll throw up all these terms. And this is called the low, like the low value approximation for e to the minus x. So the approximation is that e to the minus x is approximately equal to 1 minus x. And why am I doing this? Because each factor here is 1 minus something, 1 minus something, 1 minus something. So this is like kind of like x, this is kind of like x. So by the way, I would never ask you to derive this. Like we're just doing this to understand what's going on. But this is one of these things like, I mean, I think for a week, yes, I would expect you for a week to answer this. Like for the year, like this calculation, like, yeah, it's a little bit more than what I expect you to do in general, but it's kind of like good still to see it. So, so this can be approximated as 1 times 1 minus x, 1 minus, oops, this is x in this context. So that would be e to the minus x. So it's e to the negative 1 over 365. And the other one is, this is the new x for this approximation. So it's e to the negative 2 over 365 times e to the negative n minus 1 over 365. So what we're doing is replacing these factors, approximating these factors by these exponentials. And what's the advantage of doing this? What's the advantage of what do you get for what's the nice thing about multiplying exponentials? How do you multiply exponentials when the base is all the same?
Just add up whatever the power is.
Yeah, you just add the exponents, right? So this one is not, I mean, this one makes no difference. So it's like e to the minus 1 over 365 minus 2 over 365 minus blah, 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 minus n minus 1 over 365. So you notice that the 365 is the same in all the fractions. There's an overall minus sign that you can also factorize. So it's e to the minus 1 over 365, 1 plus 2 plus blah, 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 plus n minus 1. So you, I mean, there's a formula for those of you who have seen it for like the sum of the first n minus 1 integers. This is like the famous formula. The sum of the first n integers is n times n plus 1 over 2. So this one for the, I mean, you don't need to know this formula, but there's like a, I'm just saying there's like an actual formula, a closed formula for what this is. So it gives you n minus 1 times n over 2. Okay. So this, all of this probability can be approximated by e to the minus n minus 2 over what is 365 times 2, 730. Okay. And then you want that to be less than 0.5. And that's how you, how do you solve an inequality involving exponentials? You take the natural log. So you want the natural log of this, you know, of e to the minus n. Well, I mean, yeah, so there are different ways. I mean, you can also write 0.5 as e to the natural log of 0.5. And the exponential is an increasing function. So you just want minus n times n minus 1 over 730 to be less than 0.5. Am I doing something here? Yes, this is fine. Yeah, I think I'm making a mistake in terms of the, I think I made a mistake with the signs, or
When you took the natural log on the left side, did you also do it on the right side? Is that what it is?
no,
Or-
yeah, like, so I did like, now I did something very silly here. So it's just because you have to be careful, because everything is like the ln of 0.5 is negative, right? So let's see if I did this like the right way. No, the bases are the same, yeah. So it's just that let's see, I'm doing, okay, no, this is fine. Like, what am I doing here? So would you apply ln? Yes. Oh, okay. Yeah, it's, let's see if it's better if I take yeah, I mean, if you take ln on both sides, oh my god, I cannot believe I'm dying on the last step, which is just always work on your pre-calculus skills. So right, because ln is an increasing function, that's fine. So you get that minus n over m minus 1 over 730 should be less. What is ln of 0.2? Let's say ln of 0.2, or sorry, of 0.5 is minus 0.69. Yeah. Now this looks better. So when you can multiply by both sides by -1, and when you multiply by -1, that changes the inequality. Okay, this looks a lot better. And then you solve this inequality on Wolfram alpha, and you put n times n minus 1 is greater than over 730 is greater than 0.69. And if you put that on Wolfram alpha, you get I mean, in Wolfram alpha, you get that n it starts at 23. So it tells you that n is less than. I mean, it's like a strict inequality. I mean, it's actually bigger or equal to than 23 in Wolfram alpha. I can actually show you that so that you believe me. I mean, I guess like, yeah. N times n minus 1 over 730 has to be greater than 0.69, and that starts with and it has to be greater than 22.94. So 23 is the first one that works. Is that making sense? I mean, it's kind of like, it's like a very cool, I mean, it involves so many interesting ideas, I think, this birthday paradox. So that's why I wanted to, so it will be quadratic, exactly. So it kind of grows like as a square root. So with 365, that's a good, actually a good place to end. Like, so what is the square root of 365? It's 19, but it's roughly close to 23. I mean, so basically the bigger the number is, the more days the year has, the better this gets closer to square root. So like if the year had like 10,000 days, the square root of 10,000 is 100. So 100 should be more or less okay. And that's why, if you remember, like the birthday paradox, for 10,000, 119 was relatively okay. So it grows like with the square, like, yeah, the group of people that you need is more or less the square root of the number of days in the year. That's a better approximate. That's more and more accurate. The more numbers, you know, the more numbers you have in a year, because then the approximation of these products with the exponential gets better and better. So the reason, like, just to finish for today, because we're almost done, we only have like 3 minutes left. Let's see if this works. Okay, yeah, just to finish for today. So the reason why we did like this more or less work is because 1 over 365 is already a small number, and that allows me to kind of forget about everything here. I mean, you won't need to remember this formula, I guess. Yeah, if you ever need it, I'll make sure to, like, I'm not expecting you to rederive this result. I just wanted to do it in all detail so that you'll see all the different ideas that come into play. But yeah, like an approximation like this, I would give you, oh, hint, approximate 1 minus x with e to the minus x or something like that, if we ever encounter something like this. But the only thing that I wanted to say to finish today is like, right, the thing is, like, the more days a year has, this becomes smaller, and so this becomes a better approximation. So this is where you see at play the thing that I was saying, that the more number, that's that's why probability in a way kind of works very well when you have large numbers, because like certain approximations and things like that, they just become more accurate. Okay, but this is like a very elegant way to see the answer instead of like doing like a crazy product. I mean, this is like a brutal thing to do. Like, you don't want to do this. This is like a very elegant thing to do, but granted, you have to think about that. Okay, but I think this is a cool place to stop. I'll actually give you like a YouTube video where you can watch more about this if someone wants to still develop intuitions, and I'll send you the link for this birthday paradox website, because it explains all of this in great detail. So it's nice to read through it. But I think I'll see you on Friday, and I will send you the information about the quiz in a couple of minutes.
Is the quiz just going to be like tonight? We should submit it, or how is it?
Kind of like some examples, well, similar to the ones we were doing before the birthday paradox.
I see. Gotcha.
I'll send a list from the PDF which ones you should pay attention to. But yeah, it will be more like on the lower level difficulty, like
Okay.
the pre
Well, no,
birthday.
Sorry, I was just checking, like, is it due tonight or is it?
Oh, no, it will be during class on Friday.
I see. Okay, cool.
Yeah. It will be like kind of like the last 20, 30 minutes. Yeah.
Sounds good.
Okay, good. See you.
Thank you. Have a good one, Professor.
Bye. Have a good one. Yeah.